A robot is a machine, especially one programmable by computer capable of carrying out a complex series of actions automatically. In recent years, robotics has been implemented in various fields, whether it is in production line, medical industries, F&B, and even housekeeping. Due to this fast development in robotics, human-robot interactions, or HRI, have become more common in our community. Assalamualaikum, greetings. My name is Ifan Fikri, and I want to elaborate to you on my fascinating article titled Gesture Control for Existing Mitsubishi Robots Supervised by Dr. Tanvi Saleh. So the focus of this article will be mainly revolve around Melfa type industrial robot produced by Mitsubishi. And let me tell you something, this type of robots are usually operated through two methods. The first method is through software developed by Mitsubishi itself, and the second one is through touch pendant as in the following video.
And the robot's activated. So if you see the robot, we're going to move it. We're going to use an axis like this.
This method of controlling the robot is okay, but it is time consuming and inefficient if the robot is being utilized and calibrated frequently. Hence, we come up with a problem statement as in the following. The problem statement stated that we targeted the collaborative robotics industry community to implement the intuitive communication method because we want to allow both human operators and robots to communicate with each other in a more natural way and increase in speed and efficiency in completing a task. So what we mean by intuitive communication method is there are two types of intuitive communication method, which is the first one is through voice recognition, and the second one is through gesture recognition. Scrutinizing the area of research, we decided to proceed with the gesture recognition system and did some literature review. From the literature review, we have come up with this pie chart. As you can see, the Kinects are widely used due to its depth sensor calibrated with the RGB camera, and also Microsoft provided an SDK software development kit that will provide all 26 joints on the body for the operators to develop an algorithm to recognize what gesture the user is being shown. And as you can see, the webcam edges the Kinect sensor as the most commonly used devices for gesture recognition. This is because Kinect sensor has limited availability and expensive in the current market. So considering several factors such as cost, availability, data processing complexity, and popularity among researchers, we decided to follow the majority of the researchers in choosing webcam as the gesture recognition devices. An overview of the system design for this research is as in the following sequence. Firstly, we obtain the gesture data, and then we convert the gesture data to robot commands, and then finally we send the commands to robot. Next, we come up with a system architecture of the following. Firstly, the image frames from the webcam are obtained and sent to the gesture recognition module. And then the gesture data that has been translated by the gesture recognition module will be sent to the real-time robot positioning module, and the real-time robot positioning module will send position feedback or robot commands to the robot controller, and the robot controller will move the robot. The robot controller will also give positioning feedback to the real-time robot positioning module. And to communicate between the robot positioning module and the robot controller, we will develop the real-time robot positioning GUI in Windows form in C++ CLR language, and we will need to establish MXT command in the robot controller to create UDP communication sockets. And the gesture recognition can be divided into two methods. The first method is the convex hull algorithm, and the second method is the convolutional neural network, which is a deep learning algorithm. Both of them are widely used by many researchers. Firstly, we implemented the convex hull algorithm. In convex hull algorithm, or also called the gift wrapping algorithm, firstly we segmentate the skin, and then we filter out the noise, and after we filter out the noise, we identify the contour, and from the contour obtained, we'll find the convex hull, which is the line that is wrapping the contour, and convexity defects, which is indicated as the dot in the most right picture of this slide. And then for gesture 1 and gesture 0, there will be no convexity defects. In this case, we calculate the error ratio, which is calculated by the following formula: hull contour area minus hand contour area divided by hand contour area times 100. And for the convex hull algorithm, there are several problems. One of the problem is that it can only be implemented on simple background, and the background cannot be as the same color as the skin. And as you can see from the video and pictures, uh, the gesture data that obtained from complex background will fluctuate a lot and is not as accurate. So we decided to move on to another method, which is the deep learning framework. For this method, we developed the program in Python environment, and we use the MediaPipe deep learning framework. And from the MediaPipe deep learning framework, it can detect hand joints. It will return hand joints as in the most bottom right of the slide. It will return the joints number 0 to 20. And then we calculate from the joints, we can calculate the distance from the palm to the tip of the fingers. And to calculate the distance, we firstly find the joint distance in x-axis, and then we find the distance in y-axis, and we use Pythagoras theorem to find the total joint distance. And from this distance, we can identify which fingers are being lifted and how many fingers are being lifted. To transmit the gesture data from the external program, which is in Python environment, we implement a TCP sockets, transmission control protocol. Firstly, the robot positioning program will create the sockets and ready to receive any clients, and gesture recognition program will be the client to send the gesture data to the robot positioning program. So it will be implemented in two threads. The first thread is the communication to communicate between the robot positioning program and the gesture recognition program, and the second thread will host the robot positioning program and robot controller communication. So there are limited number of variation and various number of robot commands. Hence, we have developed an option menu which can be controlled through gestures. And from this menu, this is the research gap, and which from limited number of gestures, we can translate it into various number of robot commands. And another feature is that you can save the coordinates of the robot through gestures, and a text file will be generated to be copied and pasted into the RT toolbox. And here is the communication flow between robot positioning application and robot controller, which is established through UDP sockets and UDP communication. The robot positioning program will send UDP packets to the robot controller, and the robot controller will send back the position feedback of the robot to the robot positioning program. And this is the final GUI design. The interface for gesture recognition is as the following. As you can see on the left side of the slide is the interface for the convex algorithm, and on the right side is the deep learning framework algorithm interface. And the experimental setup is as the following. Image acquisition is done through the Ausdom AW651 webcam, and hardware specification for the PC is the Intel Core i7 10th generation CPU, 16GB RAM, and 2.9 GHz clock rate with no GPU. And here is the picture of the experimental setup. And we have done several experiments to evaluate different aspects of the algorithm, of both algorithm. And the first experiment is to identify the system consistency, to identify whether the gesture recognized from the both algorithm either fluctuate or not. So for the system consistency, firstly we show each gestures for 30 seconds, and the correct gesture detection were calculated in time frame, in period of time. For example, if I show 0, it will detect how long will detect 0 before it fluctuates to another value. And the formula, as you can see, we calculate the consistency through the formula in the middle of the slide. 1 minus 30 minus correct gesture detection period divided by 30 times 100. And on the left side of the slide, you can see is the table result for the convex hull algorithm. For gesture 3, we get the lowest consistency rate, which is 73.3%. And on the right side of the slide is the deep learning framework consistency result, which indicates that the algorithm for deep learning framework have a very high consistency. For the second experiment, we did an experiment to evaluate the accuracy aspect of the system. And we firstly show the gesture from 0 to 5 for 40 cycles. Each cycle is like 0, 1, 2, 3, 4, 5. And we did it repeatedly for 40 times. And each detection each gesture detection, the first gesture detection were recorded and put into the truth table. On the left side is the truth table for the convex hull algorithm, and on the right side is the truth table for the deep learning framework. And as you can see, both algorithms produce a similar output, meaning both of the system is quite accurate. And finally, we want to evaluate how the system will replicate the movement shown by the gesture through the RT toolbox. For the experiment, first we move the robot, we list a series of tasks. As you can see from the left side of the slide is the list of tasks from task 1 to task 4. There is for each task we want to move from a coordinates to another coordinates, and from each task were done through gestures firstly, and then each task from each gesture from the robot movement done through gesture, we will save the coordinate, we will record the coordinate and save into the text file that I mentioned earlier. And then from the text file, we copy the commands and positions from the text file into the RT toolbox and replicate it. And from the movement through RT toolbox, we produce an oscillograph to show the movement of the robot in relative to time. And as you can see in the oscillograph, if you observe carefully, it can perform the task quite accurately, and it did very well in replicating the movement of the robot movement that is controlled through gestures. And there are several system problems and restrictions for the convex hull algorithm. The first problem is it needs to be done on simple background. If it is done on the complex background, the result will fluctuate a lot and it will not produce an accurate result. And the second one is that fingers must be apart from each other. On the middle of the slide, you can see on the picture the user actually show 4, but the gesture detected is 3. This is because the middle finger and his ring finger is not too apart from each other. And for the deep learning framework, the only problem is that on startup, to establish the communication, the TCP communication or TCP sockets between the robot positioning program and the gesture recognition module, it will take around 35 seconds, which is quite lengthy. That is the only problem for the deep learning framework. For the overall system problem and restrictions, the first problem, as I said earlier, there is a limited number of gestures in comparison to the robot commands, which is in total about, for this experiment, is about 19 commands. And the second problem is that the system is unable to record sequence of movement, meaning that it can only detect coordinates. But it cannot record the coordinates and the time frame that the robot movement done during when it is controlled through gestures. So the conclusion is that robot can be controlled through gestures and it can be implemented easily. But for my suggestion, instead of using the conventional method of convex hull algorithm, we should move on and implement the CNN or deep learning framework to control the robot. And for my suggestion in future works, firstly, I want to suggest to implement dynamic gestures. In this research, we did static gesture. For example, 0, 1, 2, 3, 4, 5, it's all static. But for dynamic gesture, we can just swipe left, up, or right, and it will translate into different commands. And then second one is workspace mapping. So for this, we will need 2 stereo cameras, and it will map a 3D map of the workspace. And then if the it can detect the exact position of the hand, and if the operator point at a certain point in the workspace, the robot can move to that point. And then lastly is two-hand interface, which will uh, counter the problem of limited number of gesture variations. I hope you enjoy my presentation, and thank you for listening. That's all from me. Thank you.